Hello, and welcome to my video on volume by disk method day 2. So in this video, we're going to take what we did in our last section, which was again volume by disk method day 1, and we're going to build upon that. In that section, we did revolving problems where we only spun regions around the x-axis or the y-axis. So now we're going to move that axis around. So when we talk about a horizontal axis of revolution, we are referencing either the x-axis, for example, or maybe like y equals 1 or y equals -3. Those are all horizontal axes. So when that happens, we want everything with respect to x. That's important. So we're going to have pi integral from a to b, what I call r of x, or just really r of x squared dx. And we talked about in our last video why we have this, because area equals pi r squared for a circle. And when we do a revolving problem, at least for now, we're going to have these perfect disk or circular shapes. Okay, so our function is in terms of x, and our limits are also in terms of x. Sometimes I put like x equals here to remind you these are x values. Now, the difficult part is oftentimes the calculation of r of x. And a simple way to think about this is top minus bottom, just like we saw for area. Okay, so that's nice, it's very similar, and you'll see in a couple of minutes here an example, and we'll be able to kind of talk through that. Okay, now what happens when we have a vertical axis of revolution? So something like the y-axis, for example, which we did in our last video, or maybe x equals 5 or x equals -1. Those are all vertical axes. And we want to work with respect to y. So we have pi integral from c to d of now r of y. All that means is that our function has to be in terms of y. Okay, so r of y squared. And how can we calculate r of y? You probably guessed it. Right minus left would be our calculation. All right, so here's an example. We are taking this region bounded by f of x, which is this curve right here. There's my f of x. Y equals 12, which is this line, y equals 12. And x values of 0 and 3. So we're starting at the y-axis, going to 3 for my x value. So you can see our shaded region there, our bounded region. And we're going to spin it about. So this about part means that we're going to rotate it around this line. Okay? So you'll see we're not spinning it around the x-axis now. And to the right here, you can see a three-dimensional image of what that's going to kind of look like. And what's happening is, if I imagine taking this line, if I sweep this line or spin it around this axis, I'm going to get this circular cross-section image. Okay? So we have to think about how I'd calculate just the area of that one circle, and if we integrate that function, that's going to give us the volume of our shape. Well, if we think about this as top minus bottom, bottom, that's going to be our r of x function. Okay, now, let me erase these. Why does that work? Okay, why does the top minus bottom work? Well, we know that this distance is our function 12, and this distance is our function f. So if I subtract 12 minus f, and f is always changing, so I can't just use a number for that. Like I can't use 9 or 5 or 3. The 12 is constant. So if I did 12 minus f, it gives me this space in between, this segment or this segment or this segment. And those are all of my r's, r. And r is varying, so we have to have a function for it. So we would have pi integral from a to b, so 0 to 3. We're using x values, 0 to 3, of r of x, which is 12 minus f of x. Okay, so 12 minus f of x squared dx. Remember, it's pi r squared. So let's start working through this. And this is going to be 12 minus 9 minus x squared dx. So maybe simplify a little bit. Let's see, we want this quantity squared. I almost missed that part. So this is going to be 3 plus x squared squared. And if we're going to integrate this, we want to FOIL it. This is not a u sub problem. The reason it's not u sub is because for this to be u sub, I'd have to have an x on the outside here, which I do not. So we're going to have to FOIL this and then integrate. So pi integral from 0 to 3 of 9 plus 6x squared plus x to the 4th dx. And from there, find the antiderivative. So 9x plus 3, that'll be a 2 actually, plus 2x cubed plus 1/5 x to the 5th. And we still have to apply the FTC, but I'll leave that part. That part's just number crunching. So that's an example of revolving around a horizontal axis that's not necessarily the x-axis. Okay, let's try another one. So we have these functions. Okay, we have a bounded region, and that region is stuck between these four things. Okay, so let's go ahead and sketch this thing out. So let's see. 1, 2, 3, 4, and 1, 2. Okay. So my square root function would look like this. There's my square root function. Actually, you know what? I'm going to go ahead and use a color for this. So here's my square root function. We have a line x equals 1. Here we have a line x equals 4. Right here, and we have the line y equals -2, which is right here. Okay, and our bounded region is the region between all four of these objects. So it's this space right here that we're discussing. That's what we're referencing, okay? And in this problem, it says that we're going to rotate this region about the line, meaning around the line, y equals -2. Okay, so my radius is this segment here. This is r. And here's what's happening. All these r are dependent on two parts, right? It's going to be this part, which is my root x. That's my function root x. And this part, which is actually a distance of 2. That's my r, okay? Now, if we think about this as top minus bottom, it's root x minus -2, which is root x plus 2, and that makes sense because I would actually have to add these two things to get the radius, okay? So again, from here to here, that's your root x, and then from here to here, that's 2 every single time, okay? And if I could imagine this, if I spun this thing around, I would get this kind of, I didn't really draw it very well, but I would get this circular cross-section for my solid, okay? So this is a disk problem. So pi integral from 1 to 4, x value of 1 to x value of 4. And my function is root x plus 2 squared, top minus bottom squared, dx. So again, if we were going to finish this problem all the way, which I don't think I'm going to finish the whole thing again for you, we'd want to FOIL this because it's not going to be u sub in any way. So if we FOIL, we would get x plus 2 root x plus 4 dx. Okay, and then find the antiderivative. So pi, and we're going to have a 1/2 x squared. This is going to be a 3/2 power times a 2/3. So it's going to be 4/3 x to the 3/2. Remember, this is really x to the 1/2. So you'd add 1, multiply by the reciprocal, plus 4x, and we still have to apply the FTC, which, again, I will just leave that at that point because that's just a bunch of number crunching. Okay, so if we continue on here, we have another example, and this time I have a sketch for us, but we're being bounded by these three things. So you can see that's the greenish region here, and we're spinning this thing around the line x equals 2, so this line right here. So now, because this is a vertical axis, then we have to work with respect to y, okay? So this function, yes, this is y equals x squared, but that also means this is x equals the square root of y, okay? And we're working sideways, so we're going in this direction from here to here. So this is r. Again, if I imagine spinning this thing around x equals 2, I would get this kind of circular cross section, okay? That's a perfect disk. It's a perfect filled-in circle. So now how are we going to calculate r? Well, from here to here, that's our function. That's root y. And then from here to here, that's 2. It's always a distance of 2. So if I did right minus left, 2 minus root y, I would get this part right here, which is my r. Okay, so r of y is right 2 minus root y. So again, the way I figured that out is looking at my bounded region. Okay, so what creates the boundaries? The right function is 2, and the left function is root y for my bounded region. So I do right minus left. And we want to use y values. We're going from 0 to 4. We want to use these y values. So integrate from 0 to 4 of 2 minus root y squared dy. And again, this is very similar to other questions. I'm not going to go through and finish this problem. I'm really just working on the setup here. The rest of the work could be done with just a little bit of algebra and then some integration. Okay, so let's try one more. It says find the volume of the solid by revolving the region bounded by these 3 things. So we're bounded by these things right here. Okay, and we're going to spin it about or rotate it about the line x equals -4. So again, we have a vertical axis. So that means we're going to work with respect to y. Okay, let's just go ahead and draw our picture here though. So we've got this right here. We're going to 1, 2, 3. Try to space that better. 3, 4. Let's see. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. I'm not sure how that's going to go. Okay. So let's go ahead and graph our line. So this line's going to look like this. Going to have a slope of -2. So we're going to something like this. Maybe here and here. Okay, so it looks like we're going up to 4 and down to -4. So that's my line. Y equals -2x minus 4. We're going to have also the line x equals -4. So right here. And we have the x-axis. So we're looking at this right here. So our region is just this space right here. And as we said, we're spinning it around this axis right here. Okay, so now we take our bounded region, we look at it, and we think about what's the right and left. So this is the right, this is the left. So to calculate r of y, we would just do the right function minus the left function. So r of y is equal to my line. Now, my line, I have to actually solve for x. So I'd have y plus 4 equals -2x. So x equals -1/2 y minus 2. Divide both those by 2. So we're going to have our right function, which is -1/2 y minus 2, minus our left function, which is -4. Remember, this is x equals -4. This is x equals -1/2 y minus 2. Okay, so right minus left. Now, why does that work? Let's just kind of think about this again. We know, oops, shoot, I want to delete that. Okay, we know that, oh, come on. Sorry about that, guys. I keep deleting the wrong thing. Okay, we know that the distance from here to here is always 4. And the distance from here to here is always our function. This would be like our -1/2 y minus 2. So if I did the right minus the left, and this is actually -4, we're going to get that calculation between those two curves, okay, which is that r of y is what we're looking for. So we just set up our integral. We're going from 0 right here, because our region is starting at 0, to +4. We're looking at y values again. So 0 to 4 of that function. If I distribute the negative and combine like terms, I'm going to get -1/2 y plus 2 quantity squared dy. Okay, and then we would again FOIL. So we'd probably want to write this out, be 1/4 y squared minus 2y plus 4 dy. Then you would find the antiderivative, apply the FTC by plugging in the top and the bottom, and get your answer. Okay, so all these we're supposed to really finish the problem. I'm just more worried about the setup because I think we've done enough integration where we could obviously figure that out as needed. Okay, so that's actually going to be it for this video. If you have any questions, please let me know. But otherwise, thank you for watching.